Namaste and a warm welcome to this lecture on mathematical foundations for machine learning. We are in the week 12 of this course, which is supposed to be the last week of this lecture series, and in the past classes we have studied about clustering, classification, and we started with a regression. We did simple linear regression and we connected it to the Gram matrix, we connected to the least square solution that we studied in linear algebra, and we also gave a lot of nice interpretations to the matrix A transpose, the pseudo inverse A transpose A, the whole inverse into A transpose as far as the linear regression model is concerned. Now what we are going to do is we are going to look at the idea of logistic regression, and that will form the content for this particular lecture, and this is going to be the last lecture for this course. So this will be the last topic of the lecture series. So we will begin with a quick recap of linear regression, simple linear regression as well as multilinear regression, and then what we will do is we will see how do we get into the idea of logistic regression, what it means, how do we infer certain things using logistic regression, and so on, and that will complete this course. Okay. So let us get on to the idea of logistic regression, but before that let us do a quick recap of linear regression. I think in the last class you did have a good insight into the linear regression, prior to which Dr. Ashok Rao had given nice insights on clustering and classification problems and so on. So what I am going to do is we are going to look at a quick recap of linear regression. Quick recap of linear regression. So what are we going to do? What was this? Say for example, you could have okay, one let y be the response variable, and if we take y to be the response variable and we take let us say x to be the input variable or the explanatory variable, we will say input or the explanatory variable, we said we can fit a straight line based on how the data looks like. We can fit a straight line using this expression beta naught plus beta 1 x. Of course not at all times, we will have this linear regression to pass through all the pairs x comma y that we already observed. So we would say that it was basically some y hat is equal to beta naught plus beta 1 x, where beta naught and beta 1 were the what you call the model parameters. This were called the model parameters, and suppose if we have more than one explanatory variable, then we can write this y as the following: explanatory variable, we have y is equal to beta naught plus beta 1 x, x1 plus beta 2 x2 plus etc plus beta n xn. So we can write this as y is equal to beta naught plus beta transpose x, where x is in basically Rn, and beta I or beta is also Rn, so the beta vector is also in Rn. So this is what we had. So in this case, if you see both the y and the xi's, x1 etc x2 etc xn, all these guys, they are all quantitative variables. That means they actually measure some quantity. So we have some quantitative variables. In statistics you always have this, you have quantitative variables and categorical variables. You have categorical data, for example it could just be a simple male female or success failure you know, you can have what would you call, you can have multiple classes this like this. So you could actually have what are called as categorical variables, right. Categorical variables something like, let us say, yes or no, success, failure, etc. Success or failure, etc. So now what happens is, not at all times we will have this quantitative variable relation between a quantitative variable and multiple explanatory quantitative variables. So we could also have a case wherein which the output could be a simple yes or no. That means y is basically either let us say 0 or 1 from the set, where 0 denotes, let us say, failure or a no, and 1 denotes a success or S. So the output of the regression could just be these two values. Let us say the output variable could just be a 0 or a 1. A simple example could be this. I am sure many of us at some point of time would have tried to get a loan from bank. So you give all kind of documents possible for the bank, and now the bank has to decide, based on all these inputs that you give, the bank has to decide whether it can give you a loan or not. Another example could be where you have many of the students, if you see, they apply for higher studies in different universities, where in which they give different different inputs, which includes their academic qualification, like what is the score that they had in their academic tenure, and then what are the publications that they've had, what are the projects they have done, and they give their financial statement and a whole lot of things, based on which now the authorities in the university is going to give you either an admission offer or not. So the output is going to be a function of all these variables, but the output is just going to take one of these two values, which is yes or no, and that's exactly the situation that we are trying to look at. So we are going to look at a case where the output is either a yes or no. So let's look at this. So and what type of variable will have let's say just these two outputs? We have already studied in case of probability, where the Bernoulli random variable has only two outputs, namely success or failure, and if you have n independent observations of this Bernoulli variable, you actually get into the binomial distribution of n comma the proportion of success or the proportion of the failure, n comma p the proportion of success that we have. So we are going to basically model that kind of a situation now, right. So let's look at this. So recall, for a Bernoulli variable, for a Bernoulli variable, I'll say Bernoulli random variable with, let's say, two outcomes, namely success with the probability p and failure with probability 1 minus p, this is the thing that we have, the expected value of the outcome, the expected value Bernoulli random variable x I've put here. So the expected value of x, which is nothing but E of x, is equal to p itself, because I'm going to model success as 1 and failure as 0. So I'm going to have expected value of x to be p, and suppose you have n independent observations, it corresponds to a binomial scenario, right. Independent observations imply binomial scenario. Right. Now, so what we are going to do is let's take a simple case now. Well, let's look at an example 2 here, example where we say that okay, consider a person, let's say, receiving job offer from a company. Right. So, either the offer is going to be an yes or no. So, the offer is either a yes or a no. Right. Let P be the probability of getting the offer. Let P be the probability of getting the offer. So, what is in this case the response variable is basically this P. So, the response variable here. So, the response variable here is basically P and depends on a lot of inputs, right? Depends on, let's say, a experience in years, work experience in years, then academic qualification. So, here you can, these are basically different classes, you can put like undergrad, masters, PhD and so on. So, you can have academic qualification, then you can, there is always scores that are given for interview. So, we will put interview scores, etc. So, here you see that the explanatory variable. So, these are basically the explanatory variables, and these explanatory variables can be numerical or let us say they are categorical, right, explanatory variables. So, these are going to be numerical or categorical. So, now what we do is, since we want you have the output which is yes or no, the explanatory variables could be as to fit a model here, and that model that we try to fit here is basically what we call as logistic regression model. So, what we do is we will come to this logistic regression in a bit. We will just try to find out what it is, but then okay. So, let us do this. So, we use logistic regression in such cases. Regression in such cases, or logistic regression model in such cases. Okay. So, let us try to understand what this logistic regression is. So, let us to understand logistic regression, we begin with the idea of odds in a binomial distribution. Now, what do we mean by odds? We are going to look at that. Say, for example, you do a survey, let us say, okay, let us consider this example. Consider the survey of say 200 people who who have visited a new restaurant. So the survey is about whether they would recommend. The survey is aimed at knowing. The survey is aimed at knowing if they would recommend the restaurant to their friends. Right. Now, when they did the survey, assume that there are about out of 200 people, of the 200 people, of the 200, let's say 150 responded with a yes. Right. Now, what we are going to do is we are going to define the odds. So, what we are going to do is we are going to look at this. See, first of all, we must remember that the survey of 200 people that is drawn, it's basically from a population. It's not that only the 200 people is the population. From the entire population, 200 people have been were drawn, of which 150 of them said an yes. That means now the proportion of people who would recommend this restaurant to their friends is basically given by 150 by 200, which is an estimate for the proportion of the population which would actually say yes to this restaurant, right. So this is basically from the population. If from the population, the proportion is going to be, let's say, P, where in which that will be the proportion of people who would recommend this restaurant to their friends. But however, we will not be able to do the entire population survey. So what we do is we take a survey of 200 people, and in 200 people 150 have responded with a yes. So what we are going to say is this is called the sample proportion. So we are going to define something new here. We say that let P hat be the sample proportion of what do you call, of people who responded with a yes, who responded with a yes among the 200. Now what we are going to do is we are going to say this, let P be the population proportion, that is the entire population proportion, which says population proportion that would respond a yes for the survey, that would say yes as a response to the survey. Right. And typically you would do like all this hypothesis testing and other things, where you would use P hat to check whether this is going to be the representative of the population proportion and so on. And now what we are going to do is we are going to define P hat. So what is P hat? The total number of people who responded yes by the total number of people who took the survey, which is nothing but 150 by 200, which is 3 by 4. So now what we are going to do is we are going to define odds. Odds is equal to the ratio of proportions of the two possible outcomes. So, how are we going to define this? So, odds is equal to say for example, if p hat is the proportion for one outcome, then 1 minus p hat will be the proportion for the other outcome, right. So, p hat proportion for one outcome then 1 minus p hat is the proportion for the other. For the other. So, odds are nothing but odds of S, we will put it that way, odds of S is nothing but p hat divided by 1 minus p hat, and the odds of no is given by 1 minus p hat divided by p hat, right. So, in our example that we have taken, in this example odds of S is p hat is 3 by 4 by 1 minus 3 by 4, which is nothing but 3 by, it is basically 3 by 4 by 1 by 4, which is nothing but 3:1. So, the odds in favor of S is basically 3:1 and odds in favor of no is 1:3. Now, we do one more thing here. So, we see that the odds is given by p hat by 1 minus p hat. Now, therefore, what we will do is we will say odds into 1 minus p hat is given by is equal to p hat, which implies odds is equal to p hat into 1 plus odds. Therefore, given the odds, I can find out the proportion which is given by odds by p hat is equal to odds by 1 plus odds. So, this is another important relation that we need to know. Here we have this. You can always find this out, 1 by 1 plus p hats. Now, what are we going to do? How are we going to link all? Recall, we are just going to do one more recall here. So, recall in linear regression, what we did was in simple linear regression, the model that we used, the linear regression model, the model supposes a straight line relation between the expected value or the mean value, between mean value of the response and the explanatory variable. Explanatory variable values, right. This is what we had. That is, we said mu y is equal to expected value of y is equal to beta naught plus beta 1 x. This is what, if you remember, we did this when we did linear regression. We were basically looking at this. We already defined that this is going to be exactly for any value of x, y is a random variable with the expected value of y is equal to beta naught plus beta 1 x. So, we have already seen this before, and that is exactly what we are doing here. Suppose when y is a 1 or 0, here the response variable is basically a binary random variable or a Bernoulli random variable with y is equal to 1 or 0. The mean of y, the mean mu y is equal to the probability itself, mu p of success or p of 1, which is p itself. Now, this is going to be something which we will use. So, expected value of y. So, we want to look at the probability. So, what we are going to do is we are going to use this idea to get our model built. So, what we are going to say is the expected value of x is in this case is just p itself. So, what we will do is we will start working with this. So, what is the model? So, we are going to say p is equal to beta naught plus beta 1 x. This is what we would ideally want to do, as in the case of linear regression, right. But there is a problem. So, this is basically if we map linear regression, we do this. Okay, let me write this clearly. We try to relate, use this relation between p and x. But remember, or this whatever p hat that we had, p hat or p whatever that we had, it is going to be okay beta naught plus beta 1 x, and p is defined as the probability of the success and 1 minus p is the probability of failure. Now, what happens is, if you do this beta naught plus beta 1 x, x can take any value on the real line. Now, therefore, the value of p is no more a value between 0 and 1, right. So, let us look at this. When so, if beta 1 is not equal to 0, then p will take values outside the range, outside the interval 0 comma 1, because extreme values of x can cause this value of p to go completely uncontrolled. So, what we say is outside the interval 0 comma 1. Now, remember this, keep it in mind that remember p is a probability value, and it has to necessarily be therefore a value between 0 and 1, right. But now, when you fit a linear model here, this is going to be really a problematic one, because the probability is going to, the value of p is going to be outside the range 0 and 1. So, what we do is this is exactly where the logistic regression comes. So, the logistic regression here, overcomes this by transforming the odds using natural logarithm. Now, what does that mean? Natural logarithm, what does that mean? That means we are going to look at log of odds, right. We are going to look at log of odds, and this basically is called the log odds, or there is a name for this. This is called logit. Right, the log of odds is basically called as your logits. Now, what we do is we are going to model this log odds. Instead of modeling this direct linear relationship like this, what I am going to do is I am going to model the log odds as a linear relationship. So, what we will do is we will do this. We model the log odds as a linear relationship. Now, what does that mean? We are going to look at log of p by 1 minus p is equal to beta naught plus beta 1 x, right, and we use what do you call, we use the natural log here. Okay. So now what happens is, this is the logistic regression model that we are going to use, where this basically is the model which is going to give you values between 0 and 1. So what you do is you fit a threshold now and you get the probability value. If it is going to be beyond certain value, you say that okay, the answer is a yes, and if the value is going to be less than this, you are going to say I mean here from this you can again compute, right. You can take e power this one, you can take p by 1 minus p is equal to e power beta naught plus beta 1 x, and from there you can get the value of p, right. So that is exactly what we call as our logistic regression, which is used to kind of get what do you call the proportion or the probability, the chance of whether you are going to give a loan to somebody or not, you are going to give offer to somebody or not, and so on. Okay. So let us actually get into some kind of interpretations, and I am using this material posted on the X page of Tivadar Danka. He has this book Mathematics of Machine Learning, which is pretty interesting book, and in this he basically even looks at a wonderful material that's basically given as far as logistic regression is concerned. To understand what logistic regression does, all we need to do is we need to look at this. Say for example, I have let's say I have this basically let's look at like just two classes. So we have, so the example that we take is basically the number of hours that you put for study and the result that you get, whether it is going to be a pass or fail. So what we have is, we are just going to have two classes. Let us say you have one class which corresponds to a fail and the other class which corresponds to a pass. So I have these two, right. Now what I need to do is I need to check I mean where am I going to put the threshold and a whole lot of things. So what I will do is I will basically look at this, right. So this is basically a sigmoid function that you have. Many of you would have heard about sigmoid function, which says that sigmoid of a x plus b is given by 1 by 1 plus e power minus of a x plus b. Now how is this, so what does this function do, how does this work? Let us look at this. So let us say that we have this is basically the sigmoid function. So what we are going to do is we are going to look at this simple idea of whether we are going to, so we are going to look at a simple case example, the number of hours that you study, number of hours studied versus the result, right. You put more number of hours and then you want to check whether somebody passes or somebody fails. So you basically have two classes like this. So you put you can look at this. So I have number of hours. So this is basically my number of hours of study, right. And I am going to have, okay, this is all going to be there, and let me take this. So if it is this, all the purple ones that you have, this is basically pass, and the red ones that we have is basically fail, right. On this axis we have right. So what we do now is we basically look at so we have this, so we need a model which would basically output a 0 or a 1 So, or between 0 and 1. So, we need, let us look at this. So, from this is going to be the thing we have. We need to get a model that outputs a value between 0 and 1. The probability values are between 0 and 1, a value in 0 comma 1. This is what we have. So, now what we do is we can use our sigmoid function. What we will do is we will say sigma of Ax plus b. In our model we have used beta naught plus beta 1x. So, we could actually use the same thing. So, what we will say is sigma of beta naught plus beta 1x, if it is greater than, let us say 0.5, we say that the we predict, we say it is a pass. That means we predict it is a pass. If it is less than 0.5, we say fail. Okay, so how do we get this in mathematics? So, we are going to say sigma of beta naught plus beta 1x is nothing but 1 by 1 plus e power minus of beta naught plus beta 1x. So, what is the, so what is this, we will get into this idea of logistic regression. So, logistic regression basically uses, so logistic regression is simple linear regression plus sigmoid. Simple linear regression plus sigmoid. So, what we first do is whatever data that we have, we fit a straight line. So, what we do is, how do we go about this? So, first, so logistic regression so first apply the transformation y is equal to beta naught plus beta 1x. Now, if we do this for the set of points that we have, we basically get a straight line. So, we have this. So, let us assume that this is all what we let me just use the same color code. So, we had this. So, this is basically the hours of study. So, where I am going to put these guys, and then this is going to be my, so this is the pass probability. We have this 0, 0.2, 0.4, 0.6, 0.8 and 1, and then we can put numbers here, say 0, then we have like let us say 10, 20, 30, you can put your number of hours that you want here. Okay. Now, what we do is, the first thing that we do is we first of all do this regression, which is basically y is equal to beta naught plus beta 1x, which is going to give something like this. You may get a straight line which looks something like this. Let us take up this. So, the line could be like this, right. Now, this Ax plus b, or the beta naught plus beta 1x, is basically what we call as the logit. In this case, we call this as the logit or the log odds we have studied. So, what we say is positive logit implies, we will come back to this. This positive logit implies pass and fail. We will just get back to it in a minute. So, positive logit implies a pass, negative logit implies a fail. Now the best part is this logit value is still a value on the line that we have, it is still a value on the line, it is not at a probability because the line is going to be a real line and it is going to take all values between minus infinity to plus infinity. So we will not be able to do anything here. So what we will do is we will try to take up exponential of this logit e power, let us say beta naught plus beta 1x. Now if you take e power beta naught plus beta 1x, it would always be positive. So what we will say is this is always positive, right. Once you say that this is positive, but the only thing is this is it is of the form e power x. So e power x is going to be, you know, what do you call, a curve which is going to increase exponentially. Now what we will do is we will just flip this to get e power minus of beta naught plus beta 1x. That value is going to e power beta naught minus of beta naught plus beta 1x. This is going to have, so this is a curve which kind of sets up to approach 1 asymptotically. Now what we want is like, okay, we have this, so there is a problem now here. What is that? When you take what we call, when you just take 1, okay, e power minus of ax plus b, okay, let us do this. So we add a 1 to e power minus of beta naught plus beta 1x, 1 to e power minus of beta naught plus beta 1x. So what you do, it basically so to prevent division by 0 in the following. Okay, and that also and keeps the value, keeps the reciprocals between 0 and 1. So what do we get? The reciprocal is basically this. So we have 1 by 1 plus e power minus of beta naught plus beta 1x. This is what we have. This is going to be the value of p. Okay. So this is equal to p now. You can say that, okay, when again you can keep a threshold here when it is 0, when the factor beta naught plus beta 1x plus fellow is 0, you have 1 by 1 plus 1 by 2. So you can keep a threshold of half and say that this is beyond this is going to be pass and below that is going to be a fail. So one more thing, so this is basically how a logistic regression works. It turns the log odds into, you basically do log odds and then you get the probability value. So this is basically the idea of logistic regression, especially when you want to do a binary classification stuff where straight line is not going to be the approach. The data is going to be clearly kind of into two classes. You just want to classify them based on certain threshold. Of course you can look at the geometry and a whole lot of things here. So we have this, so the decision boundary will be a plane in 2D, then you will have higher dimension could be in a higher dimension this decision boundary could be something else, right. But of course what we need to do is we need to understand that this the logistic regression helps you classify or helps you what do you call, do this prediction, predict the probability of being a yes or no. That means you have a two class problem where you can do a prediction with this probability. You can classify them as, okay, if the based on if the probability value is beyond certain threshold you put them in one class, and below certain threshold you can predict it to be the other class. So, and typically you find a lot of applications of logistic regression, including ideas in biostatistics and places. Okay, so what we will do is, on this note we will wind up this lecture. So, we studied a couple of interesting ideas in the last module of this course. We studied classification, clustering and regression problems, and we also found out that if there are just going to be two categorical variables, how do I predict I mean how do I predict the probability of one class and the other, and what kind of threshold I can do. So, if there are two classes where you really cannot fit a straight line, what you do is you look at the odds and then you look at the log of odds, and then you put basically fit a straight line in the first place, and then once you fit the straight line you put a sigmoid over the straight line, and then take the reciprocal, you end up getting, okay, basically you take the sigmoid of whatever that straight line that you have fixed, you are going to get into probability values between 0 and 1 with which you can predict the class. So, with that we come to the end of this lecture series. We have looked at a lot of things over this, and we in the last module itself we looked at classification, clustering and regression problems. There is much more than what we have covered in this course. We have just tried to give a foundation mathematical ideas and insights for machine learning. I mean, you have way too many books and way too many good articles on taking this forward to higher mathematical ideas as applied in machine learning. I hope you enjoyed the course, and hope to come back to you with another course with insights. Thanks a lot for being a part of this course, and wish you all the very best. Thank you.